Reflection of light by B.N. Achar. Examples for reflection of light are innumerable. A few examples are given here: flower, scenery, bird, Taj Mahal and peacock. Different colors and images observed in these figures and everywhere in nature are all due to the reflections of light. A beam of white light is made up of 7 colors. They are violet, indigo, blue, green, yellow, orange and red. They are briefly known as Vibgaya. Observed red, orange, yellow, green, blue, indigo or violet color is equal to Vibgaya minus absorbed colors. For example, green color is equal to Vibgaya minus Vibgaya. Reflection of light. Objects are visible because of the reflection of light from their surfaces. The colors observed depend on their ability to reflect light of certain wavelengths and absorb that of other wavelengths. Intensity of the reflected light depends on the nature of the surface and the differences in the refractive indices between the two media. Greater the difference between the refractive indices, greater will be the reflection intensity. Reflection of light. When a light ray strikes a smooth surface, a part of the light returning into the same medium in accordance to definite laws. A smooth reflecting surface, AO is the incident radiation, O is the point of incidence, ON is the perpendicular line. Theta I is known as angle of incidence, which can be defined as the angle between a ray of light meeting the surface and normal to the surface at that point. OB is the reflected radiation. The angle theta R is known as angle of reflection, which can be defined as the angle between a ray of light returning back to the medium and normal to the surface at that point. Regular reflection or specular reflection and diffused reflections. An incident radiation falling on a smooth reflecting surface makes an angle theta I known as angle of incidence with respect to the perpendicular line. Similarly, the reflected radiation makes an angle theta R known as angle of reflection with respect to the perpendicular line. In the case of specular reflection, angle of incidence theta I is equal to the angle of reflection theta R. When an incident radiation falling on a rough reflecting surface produces diffused reflections which are not of much practical importance. Regular reflection or specular reflection. In regular reflection, the incident radiation AO, the perpendicular line ON and the reflected radiation OB must lie on the same plane. Then the angle of incidence theta I must be equal to angle of reflection. Further, the reflected ray and the incident ray are on the opposite sides of the perpendicular line. Thus, regular or specular reflection is governed by the 3 laws of reflection. Firstly, the incident radiation, reflected radiation and normal to the reflecting surface at the point of incident lie in the same plane. Secondly, angle between the incident radiation and the normal known as the angle of incidence theta I, which is equal to the angle between the reflected radiation and the normal at the point of incidence, known as the angle of reflection theta r. Thirdly, the reflected ray and the incident ray are on the opposite sides of the normal. Consider an interface between air medium with refractive index n1 and a smooth reflecting surface with refractive index n2. If II represents the intensity of the incident radiation and I reflection represents the intensity of the reflected radiation at the interface, then the measure of the fraction of light that is reflected by a material is called its reflectance. When a radiation traveling with an angle of incidence 0, the fraction of light reflected is given by the reflectance power rho, which is defined as the ratio of the intensity of the reflected radiation to the intensity of the incident radiation. The reflective loss at a glass or quartz surface increases slightly as the angle of incidence increases up to about 60 degrees. Beyond this angle, the percentage of radiation reflected increases rapidly, which approaches 100% at an angle of incidence 90 degrees. Reflectance power rho, intensity of the incident radiation II, intensity of the reflected radiation IR, the refractive index N1 of air and the refractive index N2 of reflecting surface are related by the following equation. Rho is equal to I reflectance divided by I intensity equal to N2 minus N1 whole square divided by N2 plus N1 whole square. Important note: greater the difference between the refractive indices, greater will be the reflectance power. Reflectance loss in the intensity of the electromagnetic radiation after passing through a glass slab. II is the intensity of the incident radiation at the first interface between air and glass media. IT prime is the intensity of the transmitted radiation inside the glass medium. IT is the intensity of the transmitted radiation at the second interface glass-air media. Reflectance losses are represented by the light-colored arrow marks at the two air-glass and glass-air interfaces. Reflectance loss. Consider, for example, index of refraction for air N1 is equal to 1.0003 and that of glass medium N2 is equal to 1.5446. The intensity of the transmitted radiation at the first interface of air and glass media can be calculated as follows. Rho is equal to N2 minus N1 whole square whole divided by N1 plus N2 whole square, which is equal to 1.5446 minus 1.0003 whole square whole divided by 1.0003 plus 1.5446 whole square, which is equal to 0.0458. Intensity of the transmitted radiation IT prime at the first air glass interface IT prime is equal to II minus IR equal to II into 1 minus rho equal to 1 into 1 minus 0.0458, which is equal to 0.9542, since rho is equal to IR divided by II. The intensity 0.9542 of the transmitted IT prime will be the intensity of the incident radiation at the second glass air interface. If the glass slab is of small thickness, 1 centimeter or less, it can be considered as a good approximation, as the refracted radiation at the first phase transmitting with an angle of refraction equal to 0. So rho is nearly equal to 0.0458 at the second glass air interface. Then the intensity of the transmitted radiation IT after passing through the interface of glass air media can be calculated as IT nearly equal to 0.9542 into 1 minus 0.0458, which is nearly equal to 0.9105. Thus, 8.95% of the intensity of the incident radiation is lost due to the reflectance losses at the two interfaces. So, in conclusion, in order to minimize the reflectance losses at the interfaces, the materials selected must have difference between the refractive indices N1 and N2 as small as possible. Critical angle and total internal reflection. Let us consider a lighter medium with the refractive index N1, for example air, is separated by a denser medium with the refractive index N2, for example glass. Let theta I represents the angle of incidence, theta R represents the angle of reflection, theta capital R represents the angle of refraction, and the dotted lines represent normals to the interface at the points of incidences. A beam of light from a source incident with an angle of incidence theta I. A portion of the light will be reflected back inside the medium with an angle of reflection theta R, which is equal to angle of incidence theta I. Another portion of the light will be refracted with an angle of refraction theta R, which is greater than the angle of incidence theta I. As the angle of incidence increases, the intensity of the reflected radiation increases and the intensity of the refracted radiation decreases. When the angle of incidence theta I corresponds to the angle of refraction equal to 90 degree, the angle of incidence is known as critical angle of the medium, which is represented by theta C. Any angle of incidence greater than the critical angle of the medium delta C, total internal reflection is taking place. Important notes. 1. Intensity of the reflected radiation increases as the angle of reflection increases. 2. Intensity of the refracted radiation decreases as the angle of refracted radiation increases. Conditions to be observed for the critical angle and the total internal reflection. 1. The ray must travel from denser medium to rarer medium. 2. The angle of refraction theta capital R must be equal to 90 degree corresponding to the angle of incidence theta I, which will be now called the critical angle theta C of the denser medium. 3. The angle of incidence theta I must be greater than the critical angle theta C to observe the total internal reflection. How to calculate the critical angle? The critical angle theta C for the denser medium with respect to the lesser denser medium air can be calculated using the following equation. Theta C is equal to sine inverse of 1 by n, where n is the refractive index of the denser medium. A few examples are given in the following table. It will be seen that greater the refractive index of the denser medium, lesser will be the critical angle of the medium. A few important applications which use the principles of critical angle and the total internal reflection. 1. Diamond cutters cut the faces of diamonds so that the light entering the diamond undergoes total internal reflection. 2. Construction and working of fiber optic cables used for phones, computers, TVs, etc. 3. Periscope. 4. Prismatic binoculars. 5. In the construction of endoscope, which surgeons use to see internal organs during surgery. 6. SLR cameras, etc. Thank you.